This research explores the energy and training data requirements for supervised learning of MM-mode linear optical circuits using coherent states, with the goal of identifying the modes on which a linear optical unitary acts non-trivially and learning its action on those modes, referred to as the KLOJ problem. Linear optical circuits play a crucial role in processing photon-encoded quantum information and photonic information processing, as they are used to construct complexity for production of photonic or continuous variable cluster states essential for optical implementations of measurement-based quantum computation. A hybrid quantum classical algorithm is employed, utilizing coherent state inputs and continuous variable swap tests to compute and minimize an empirical risk function. Two schemes are considered for allocating total energy E to the learning algorithm. One where each of T random training coherent states has energy E, T, and another where a single random MT mode coherent state with energy E is partitioned into T training coherent states. The latter scheme exhibits a polynomial advantage in training data size sufficient for convergence of the empirical risk to the full risk, attributed to the concentration of measure on the 2MT1 sphere. Generalization bounds are proven, indicating the sufficiency of O, E caret 1/2 M training states in the first scheme and O, E caret 1/3 M caret 1/3 training states in the second scheme. The KLOJ problem is analogous to learning quantum K juntas, where a linear optical K junta corresponds to a K qubit subregister. This work provides an energy-efficient, adaptive algorithm that identifies the junta set and learns the circuit. The use of coherent states as training data is motivated by the transitive action of linear optical unitaries on isoenergetic coherent states. Measurements obtained from these coherent states are utilized to estimate the matrix elements of the target linear optical unitary. The learned parameters often correspond to discrete structure specifications and interaction strengths, offering significant improvements in training data requirements. This approach is a type of continuous variable quantum process tomography, and its broader implications for characterizing linear optical circuits and photonic quantum neural networks are emphasized. Unlike previous methods, the hybrid quantum classical algorithm uses coherent state inputs, enabling efficient and adaptive learning of linear optical K juntas. Linear optical K juntas, KLOJ, are orthogonal matrices in O, 2M, SP, 2M, R, that preserve a subspace K of dimension 2M2K and can be represented as a direct sum of the identity and a 2K dimensional symplectic matrix. In continuous variable, CV, quantum information processing, KLOJ are intimately connected with quantum K juntas. Specifically, if a unitary U is associated with a KLOJ, it acts as a quantum K junta on a specific set of MCV modes. The empirical risk minimization problem for learning general linear optical unitaries is formulated using coherent states as training data. The empirical risk function measures the average error between the target and learned unitaries over the training set of coherent states, guiding the optimization process in variational algorithms for learning KLOJ. Two settings, ERM1 and ERM2, are explored, differing in how the training coherent states are generated. An energetic modification to ERM1, called ERM1, enables quantitative comparison of the two training state generation methods. The generalization performance of these settings depends on the number of modes in the linear optical circuit, the energy of the training coherent states, and the size of the training set. The proposed settings and generalization bounds have potential applications in a hybrid quantum classical framework, including the use of non-classical states of light for learning linear optics. However, the problem of utilizing non-classical states for learning linear optics remains an open question, left to future work. In variational learning settings, calculating the empirical risk function is crucial. To address this, a novel method is proposed, leveraging a time delay multiplexed circuit and the CV swap test. Two approaches, ERM1 and ERM2, are introduced to enforce energy constraints on the training set. In ERM1, each coherent state has energy E, whereas in ERM2, the total energy of the training set is E, regardless of its size. The empirical risk functions, CERM1, V, and CERM2, V, are defined to measure the difference between the target linear optical unitary U and the learned unitary V. A chain of inequalities is derived, providing an upper bound for each term in the sum of the empirical risk functions. This demonstrates Lipschitz continuity of the empirical risk and full risk in both settings. The proposed method utilizes a triangular or rectangular decomposition for the linear optical unitary V, which can be directly optimized over its matrix elements. This avoids parametrization-dependent challenges in optimization, as the matrix elements of V are directly tunable due to their representation as couplings between field quadratures. The importance of considering energy constraints in variational learning tasks is highlighted, particularly when dealing with large-scale quantum systems. The ERM1 modification ensures that the training dataset has a total energy equal to that of ERM2, providing a more balanced comparison between the two approaches. This novel approach to variational learning of linear optical unitaries emphasizes the role of energy constraints and the use of time delay multiplexed circuits for empirical risk function calculation, offering a promising avenue for optimizing the learning process in quantum computing and related fields. The authors establish bounds on the difference between the cost functions CERM1 and CERM2, which represent the expected risks of empirical risk minimization algorithms. Notably, they show that the Lipschitz constant of the cost function is smaller for ERM2, implying that the cost function is more stable and easier to optimize. To derive these bounds, the authors utilize the definition of trace distance for pure states and the triangle inequality to obtain upper bounds on the differences between the cost functions CERM1 W, CERM1 V, and CERM2 W, CERM2 V. They also demonstrate that the integrals defining the full risks lack closed-form expressions but can be approximated using series expansions, similar to hypergeometric functions of matrix argument. An example of such an approximation is provided for 1 CERM1 V. Numerical minimization of the cost function reveals that below a critical value of t equals m, minimization fails to return a W that approximates the target U closely in Frobenius norm. However, at t equals m, a transition to successful learning of U is observed. This transition is attributed to the fact that a 2m×2m symplectic orthogonal matrix is a function of 2m×m block submatrices, making m linearly independent training coherent states sufficient to render CERM1, 2, a faithful cost function. The authors note that even when the empirical risk is almost always faithful, the performance of the minimization algorithm depends on how the energy scales with the number of modes, due to the energy-dependent barren plateau phenomenon. To mitigate this, they propose a modified scheme, ERM1, which requires each training coherent state to have energy E equals T, reducing the impact of the exponential factor that causes the energy-dependent barren plateau phenomenon. Additionally, they introduce an energy-efficient adaptive method for learning a KLOJ, based on the fact that if the junta set J were perfectly known, then it would be wasteful to use training coherent states that are non-vacuum on the JC modes. Empirical risk minimization is demonstrated for a uniform random 8-mode target linear optical unitary, U, with 8 uniformly random coherent state training datasets of varying sizes. The quality of the minimization output is quantified by the squared norm of the difference between the target unitary and the learned unitary, OU squared. Comparative analysis of two empirical risk minimization approaches, ERM1 and ERM2, reveals distinct performance landscapes. ERM1 fails to obtain a minimum for training datasets of size t less than 8, as expected due to the lack of faithfulness of the empirical risk for smaller datasets. In contrast, ERM2, with the constraint VI squared less than equals 10 to the power of 6 enforced on the variational matrix V, exhibits a more favorable landscape, with numerous data points achieving minimal empirical risk values. The empirical risk minimization process is further optimized using algorithm 1, which learns a target KLOJ on M modes using O, M plus K squared minimizations of a faithful empirical risk. The algorithm iteratively updates the junta set J, utilizing training sets of size t greater than equals k to ensure the empirical risk function is faithful for learning KLOJ. Numerical results demonstrate the algorithm's efficacy, with termination in the first junta set update for certain instances of U. Energy consumption analysis reveals a total energy requirement of at most M2, E2 plus, M2, E3 plus Mk plus 1, EK. This can be improved by introducing a discrete variable quantum register controlling the junta set updating procedure and applying Grover's algorithm for unstructured search, potentially allowing learning U after sublinear, in M-ERM runs. Alternative algorithms for identifying the junta set J without learning the target KLOJ are also discussed, including a semi-classical algorithm utilizing only pure coherent states, suitable for continuous variable systems. An algorithm for KLOJ learning with adaptive linear optical ansatz is presented. The algorithm iteratively updates the junta set, initially empty, based on CV swap test results between modes A and B, and C and D. This process determines whether a mode should be appended to the complement of the junta set, repeated according to energy-dependent complexity results, until the desired accuracy is achieved. Generalization bounds for learning quantum dynamics in quantum machine learning with few training data are also discussed. Concentration inequalities are crucial for bounding the probability that the empirical risk differs by a small amount from the full risk. In this context, the relevant concentration inequalities are for independent, identically distributed random variables in an interval defined by the norm of the observable defining the loss function. A Gaussian function, f, x, is introduced, which is Lipschitz on the D-sphere of radius r, where L, U, V, is a positive, symmetric matrix. The concentration of this function about its expectation, E, f, is related to the Lipschitz constant, through Levy's lemma. This leads to the generalization bounds for learning a linear optical unitary, as stated in Theorem 1. The theorem provides a bound on the probability that the value of the empirical risk differs from the full risk by a certain amount, with probability at least 1 over training sets S. This bound is essential for understanding the convergence of ERM1 and ERM2 learning protocols and the qualitative difference in the size of the coherent state training set required for convergence. The authors present two generalization bounds for energy-constrained regression models ERM1 and ERM2. The first bound, equation 18, is derived using Levy's lemma and applies to ERM2. It states that with high probability, the difference between the empirical risk and the true risk is bounded by a term that scales with the energy constraint and the size of the training set. This bound is obtained through covering the space of possible functions with a finite number of balls and applying Levy's lemma to bound the probability of the event. The second bound, equation 19, is derived using McDermott's inequality and applies to ERM1. It also states that with high probability, the difference between the empirical risk and the true risk is bounded by a term that scales with the energy constraint and the size of the training set. However, the proof is more involved and requires a different approach due to the product structure of the sphere. Additionally, the authors discuss the modified scheme ERM1, which has the same total energy as ERM2, and show that it requires OMP_E training states for generalization. They emphasize the importance of linear optical circuits for photonic quantum information processing and note that automated quantum experiment design techniques often use linear optical circuits as primary examples. The development of a novel algorithm for learning linear optical circuits is presented, focusing on optical K-juntas, a class of circuits characterized by entangling at most K pairs of modes. Two empirical risk minimization algorithms, ERM1 and ERM2, are introduced to calculate the risk of learning these circuits using coherent state training datasets with a fixed energy distribution. The authors explore the practical implementation of these algorithms in scenarios with parallel or limited access to the target linear optical circuit. The paper shows that using non-classical continuous variable CV, Gaussian states as training states can improve the sample complexity of learning linear optics. Additionally, applying a specific hypothesis class of ansatz can enhance the learning algorithm. The authors connect their work to previous studies on quantum circuits, quantum information processing, and quantum tomography, highlighting the relevance of their approach in the context of existing research. The authors acknowledge the importance of considering limitations, assumptions, and future work, such as extending the learning setting to include an entangled memory register and improving the sample complexity of learning linear optics. The implications of their findings for future research are discussed, including potential advancements in quantum machine learning and the continued exploration of the relationship between quantum computing and classical machine learning. I apologize, but it seems you didn't provide the content to refine. Please provide the transcript, and I'll be happy to help you refine it according to the guidelines you specified. I'll transform the text into a concise, direct, and technically accurate summary suitable for voiceover narration, maintaining the depth and complexity of the original content. I'm happy to help. However, it seems that the original text is missing. Please provide the original text, and I'll be able to refine it according to the guidelines you specified. I'll transform the text into a concise, technically accurate summary suitable for voiceover narration, maintaining the depth and tone of the original content.